Hi everybody. This starts to get a lot easier now because now we're just talking about precipitation processes, and precipitation is the end point after condensation. Condensation can be a cloud that stays up in the sky for weeks. Precipitation is the condensation that falls to the ground. And sometimes it does take weeks for that cloud to precipitate. We'll learn a little bit more about that. Again, precipitation is any form of water, liquid or solid, that falls from a cloud and reaches the ground. There's many droplets involved. That's what we're going to learn about today. The process of forming precipitation starts with the process of forming condensation, which involves the dew point and the condensation nuclei. It can take weeks for the surface of the condensation nucleus to build up into a typical raindrop, or it could take minutes. And the difference between those two time frames is the subject of a lot of study that you could participate in if you wanted to do some of that study for your final project. But there are two theories about how that process speeds up from weeks to minutes, and we're going to learn about the two processes. One is for warm clouds and the other is for cold clouds. The first process, collision and coalescence, is for warm clouds. It's a theory. The second process is the ice crystal process for cold clouds. So they very much describe what's happening. Collision and coalescence is many condensation nuclei with droplets forming together to make one big droplet. And ice crystal process says that the condensation nuclei attracts ice particles to it, and those ice particles attract other ice particles to it. Let's get into the specifics. For the precipitation process that involves collision and coalescence, remember it's warm clouds that the theory works on, saying that there are small cloud droplets, and in fair weather cumulus clouds, there are often downdrafts. That's why we see the blue sky between the fair weather cumulus clouds, downdrafts. These downdrafts can take some water droplets with them. When the water droplets start to fall from the upper reaches of the cloud down through the cloud, they can collide with other droplets and form bigger droplets. Pretty easy. And in addition to that, some big thunderstorm clouds have those downdrafts within the cloud and updrafts within the cloud. We'll learn more about that soon. So they form this circular pattern in the cloud where that water droplet can now get bigger and bigger by going through rotations of the cloud. That's a way that the time frame can be minimized from weeks down to hours. If you have a vertically developed cloud that has been growing in a nice clip through an afternoon, it can start to form updraft and downdraft regions that can circle these droplets around quickly and take that raindrop time from weeks down to minutes. That's the theory. But there are warm clouds, generally lower, and there are cold clouds, generally higher, up toward the stratosphere. When you see the anvil on some of these thunderstorm clouds during the summer, that is the stratosphere's bottom. And so it's cold up there. There's going to be a lot of super cooled water up there because remember, there's not a lot of dust in the upper atmosphere. So there are some ice crystals that can draw other ice vapor to it, but not very many. So it could take some time to make that happen. Let's talk about that iced vapor and that super cooled water up in the upper regions of the atmosphere. We are going to go back to our saturation vapor pressures. We move this up so you can see it. When we look at cold clouds and their saturation vapor pressure, we've talked about supercooling in the absence of condensation nuclei. I'm just going to go back to that for a second because remember, there can be supercooled liquid below freezing without condensation nuclei. I'm not saying in the upper regions there are no condensation nuclei. There's always some ice crystals up there, and those ice crystals can attract more vapor to it. Let me explain a little bit about that. This has vapor above the supercooled water below freezing, and ice has vapor over ice below freezing. So remember, temperature is average kinetic energy. There is always some vapor evaporating, and there is always some vapor condensing. They form an equilibrium that's very low over ice, that's a little bit higher over supercooled water. But what you're seeing here is that over a supercooled liquid droplet, there's more vapor. Remember, there's more vapor than over the supercooled ice crystal. Less vapor around there. Again, equilibrium, you want to come to a balance between more vapor and less vapor. More vapor is going to move to less vapor. So over time, the theory of the ice crystal theory, which is called the Bergeron theory, is that this higher pressure saturation vapor will move from the supercooled water droplets over to the ice crystal droplets. Let's see how that looks. That starts out as a relatively larger water droplet and a relatively smaller ice crystal. This is stepped art that'll go through here. And gradually you will find that the water vapor leaves the water droplet contracts because the pressure is lower, and the water vapor will go to the ice crystal. The ice crystal will get larger. This process also involves some of the collision theory with it, because of course everything has to come down with gravity. And so the theory, the ice crystal theory, also involves that the ice crystals will fall and they will collect supercooled droplets as well as they fall, and they will collide and they may fracture in colliding. So there is some collision to this theory. That fracturing can cause the beautiful crystallization that you see with snowflakes. And I think I have some examples here. Hold on a second. I'm gonna go back here. Some of the beautiful examples. These photographs were all actually taken, I believe, in the 1870s. Some of the first photographs were done literally on snowflakes before they melted, and their beauty, just absolutely stunning crystals. And every snowflake that you can find will be unique in their crystallization. Really beautiful stuff from a long time ago. So let me go back here. So that there are two theories, one for warm clouds, one for cold clouds. You can study up on that. Precipitation types. I'm going over this because some people get confused by it, and hopefully I can make it seem very straightforward. Obviously, precipitation starts as water droplets or ice crystals, depending on the temperature of the cloud, and then there is a level, a condensation level, that will predict how this falls as precipitation. Will it fall as snow? Will it fall as sleet, freezing rain, hail? Let's look into that in specifics. This is a complicated diagram that I hope you'll take a look at, and it is in your book as well. But it looks at soundings again for environmental lapse rates and precipitation outcome. So what you see here is you see a environmental lapse rate that is coming down to go to the surface, and as it comes down, it is below freezing in all places. Below freezing, the orange mark there, the red mark that you're used to seeing, below freezing, below freezing. It ends up in different places. So when the precipitation starts below freezing, it will start as snow because ice crystals form snowflakes, as we just saw before. If the environmental lapse rate stays below freezing, it will fall as snow on the surface. And if the environmental lapse rate at an altitude goes above the freezing layer, the precipitation will melt in that altitude. If it then goes back and experiences an inversion on the way down, it could freeze again before it gets to the surface. That will fall as sleet, especially when that inversion is very close to the surface. It falls as sleet. When that inversion is even closer to the surface, it falls as freezing rain. So in other words, you'll hear the sleet, right? You might not hear the freezing rain because it's not as dense. It's freezing again just before it hits the surface. If it does not come back as an inversion at all, this is more of an isothermic line here, then it will stay as rain. So take a look at that in your book. And hail, good stuff. It was just hail a week ago or so. Hail is the updrafts and downdrafts compressed into an afternoon of rotations. And hail, while you may think that it is a wintertime event because it's frozen water, hail is never a wintertime event. Hail is only during the summer. And the reason hail is always during the summer is because you need this massive cloud to give you enough space to do those rotations so that the condensation level is right here. Well, I take that back. The level of condensation is down here. The freezing level, that's where the dew point meets the environmental lapse rate. The freezing level is up here. You need a cloud that is sizable above the freezing level in order to work those rotations enough to form that hail in the rotations. That happens during the summer. The clouds are lower during the winter because there is less warm air at the surface to power them when they are putting out parcels in the afternoon. All right, let me prove to you about the rotations and the hail. What you're seeing here are circular rotations of hail growth, of going up and going down and gathering water droplets to the ice particle. So hail is a summertime event, and now you are done with chapter 5, which is a big step forward. You have covered dry adiabatic lapse rate, moist adiabatic lapse rate, stable atmospheres, unstable atmospheres, and precipitation processes. Congratulations, it was a lot to do, and I hope you learned it well, and reach out to me with any questions. Let's go on to chapter 6.